these clicky boxes. So okay, hi everyone. Thank you for joining the Astro seminar. It's a bit of a shame that we are in lockdown again, but I hope everyone's coping well. So today we have invited Dr. Toshiki Sato from Rikkyo University, Japan. Toshiki is one of my collaborators, and he has obtained his PhD at Tokyo Metropolitan University in 2018. And after that, he has moved to Rikkyo as a special postdoctoral researcher, but he spent most of his time as a visiting researcher at NASA Goddard Space Flight Center. And he specializes on observational astronomy of supernova remnants. But he also works on instrumentation of X-ray telescopes, and especially at NASA, he was working for CRISM, which is one of the big X-ray telescope projects. And since April this year, so last month, oh no, 2 months ago now, he has started his affiliation at Rikkyo University as an assistant professor. And today he will tell us about his work on supernova remnants. So please take it away.
Thank you for introduction. This is Toshiki Sato from Rikkyo University in Japan. Today I'm going to talk about X-ray observation or supernova remnant, and especially about our recent result that was published in Nature in this April, and this result was about for the Galactic supernova remnant Cassiopeia A, as shown in this figure. And in our observation, we found some result that the Cassiopeia supernova was probably came from the neutrino-driven explosions, and at least our result will allow us to prove some physical parameters around the central core of exploding star, and we think that will be very useful method to investigate the physics around the central region of the exploding star. And that paper was titled as high-entropy ejecta plumes in Cassiopeia A from neutrino-driven convection. So if we would like to know more detail, please read that paper, or we welcome they discuss directly, so please contact us. Anyway, today's our seminar's title is X-ray probing of the death of a massive star, and the first demonstration of neutrino-malaria interactions using X-rays. Then, yes, let's start. Let's start. Okay, before talking about the detailed result, here I'll explain that our X-ray observations of supernova remnants. Supernova remnants are known to be a hot plasma that was formed by shock heating, supernova shock heating. And in X-rays, we can observe highly ionized elements and their distribution in such a remnant. And yeah, we think that is a very unique tool to investigate a supernova or explosion mechanism. That is because in the case of the optical supernova observations, it is difficult to discover the shape of the explosion. But using the X-ray observation of the supernova remnant, we can see that there's morphology of that remnant. and that is a very unique tool. And for example, here I show some pictures of the supernova remnants in our galaxy. Those are very famous ones. For example, here I show the type 1A remnant, like the famous Tigris supernova remnants, or SN1006. And here we can see more circular, asymmetric circular morphology like this. And on the other hand, in the case of quark supernovae, the remnant has a more asymmetric shape like this. And in this case, we can see more filamentary structure and knotty structures. And yeah, using the X-rays, we could obtain those beautiful images, and we can discuss the distribution materials. Yes, and now we have almost 300 samples in our galaxy, but in the case of the X-rays, only 15 samples, about only 50 samples are bright with X-rays. So there is not so many samples. Even if we include the LMC or SMC samples, the sample number is up to about 30 samples or something. So we have a limited sample number, like the supernova remnants, but those are located close to us, so we can investigate the detail using those remnants. And we think those are advantage of the study of the X-ray observations. And here we would like to introduce what we can do using X-rays. We mainly have two pieces of information. One is the X-ray image, and another is the X-ray spectrum. And using both information, we could discuss what is the origin of the remnant, or we could investigate the shock physics in that remnant. For example, by using X-ray imaging, we could investigate our distribution of each element like this. This is a Cassiopeia image. We can see silicon and sulfur and calcium and iron images here. And also I showed high energy X-rays. High energy X-rays mean the synchrotron emission from the cosmic ray electrons. So using X-rays, we could also investigate the high energy phenomena produced by the supernova shock wave. That is also interesting studies. But today I will introduce only the distribution of the elements. And also we could obtain the X-ray spectrum like this. This is more useful information because here there are many we could evaluate many physical parameters using the this spectrum. For example, we could obtain the X-rays from 0.5 to 10 keV typically. Then we can see emissions from elements. And for example, in this figure, we can see oxygen, neon, magnesium, silicon, sulfur, argon, calcium, iron, like this. And using the shape of the spectrum, we could evaluate some physical parameters. Sorry, quick question.
Yeah, Ilya has a question.
Oh, thank you. Sorry, I didn't mean to interrupt you mid-sentence. I apologize. But I was trying to understand what is physically responsible for generating the signature in the X-rays. So is it specific transitions, ionization energies? What is it exactly?
Yeah, actually, the in the spectrum we can see the X lines from Xi. That we can see the hot plasma shocked by this supernova reverse shock, and then elements are excited collision with the electrons. Then transition X-rays we can see here. Then each lines are identified by the elements.
Sorry, but I guess I'm asking. So I guess my question is, so the lines that correspond to individual elements, right?
Yes.
Are these particular transition lines? And if so, I would imagine that you have a very thick forest of these lines. So unless you have incredibly precise spectroscopy, how do you manage to identify the lines with individual elements?
Typically, we have thermal plasma models to explain such a ionizing plasma. In the case of the supernova remnants, the plasma is ionizing. Then we modeling those emission, and by fitting the spectrum with the such as thermal plasma modeling, thermal model, we could evaluate what line is comes from what elements, and also then we could evaluate the ionization state from the centered energy of each lines. For example, if ionization is progressing, then the centered energy of each line is shifted to high energy, and but those parameters can be determined by the model fitting. Is that okay?
I see, and even the fact that you have these very fast ejecta. So when we're talking about 10,000 kilometers per second, for example, we're talking about 3% of the speed of light. So I expect that the lines are significantly broadened by something like 3%. Does that not create a problem? Because if each of your lines is broadened by a few percent, and there are so many lines around, I would have naively imagined that your lines just start overlapping like crazy. So I'm just amazed that you can still distinguish them, because the number of lines is quite large, and if they are significantly broadened, it's remarkable that you can still tell them apart.
That's right. Actually, it could in the younger supernova remnants has a very high velocity for the ejecta. Then we have also the Doppler shift in effect in the spectrum. And for example, if the remnant was diffuse, it is difficult to distinguish each structure with different velocities. But in the case of not the remnant like Cassiopeia A, we could separate there is each structures with different velocity. So if so using the regional analysis, then we could evaluate the velocity with fitting, spectral fitting. So we can separate those effects using the analysis.
Thank you. Sorry again for the interruption. Thank you.
No, it's okay. Yeah, thank you. Yes, yeah. Actually, as I explained now, we could also have parameters, the kinetics in the spectrum, and we could also evaluate those parameters using the spectral fitting. And so those are they're using both the X-ray imaging, the X-ray spectroscopy. We could discuss the element abundances and the plasma temperature and the ionization state. Also, kinetics are Doppler saved, and we think that those are very useful information to discuss the asymmetries during explosion, because in the young supernova remnant, in the case of the young supernova remnant, ejecta are still almost freely expanding. So the ejecta kinematics and the distribution keep some information at the explosion. So those are very unique information obtained from the supernova remnant. And here I would show you some examples of X-ray studies using X-ray imaging and the X-ray spectroscopy. And for example, in this study, this is done by Laura Lopez at 2011. They investigate the shape, morphology of the remnant and the 24 samples. Then they measure this plot. This plot shows, this axis shows a mirror asymmetry, and this axis shows elongation of the ejecta distribution. Then they also found that we have two groups. One is a blue group, blue color, and other is a red color. Then they argued that probably type 1A supernovae has a more symmetric explosions, and there's grouping probably comes from the differences of the explosion mechanism. In the case of the quark supernovae, we need some strong asymmetric effects during explosion, and there is should be appeared in the ejecta distribution at the supernova remnant phase. And yes, as seen in this plot, the distribution of the ejector are investigated by the X-ray imaging will be very useful to discuss such a asymmetric effect during explosion. Also, here I showed some results done by the Huri Yamaguchi at 2014. They investigated X-ray lines from the iron, and then they determined the centered energy of the lines and the strength of the luminosity of the lines. Then here we can also see the two groups. One is a type 1A. Type 1A has a lower central energy of iron. This means low ionized iron in the type 1A supernova. On the other hand, in the case of a quark supernovae, the central energy is more higher. This is thought to be that comes from the differences of the sounding materials. In the case of quark supernovae, there's events should come from the star forming region, and such an environment has a more dense environment rather than the type 1A cases. And yeah, those differences make these different groupings like this. And yeah, like these studies, the X-ray observation of the supernova remnant will be very useful to discuss how the progenitor flowers explode. Okay, and then from here, I'd like to introduce our background for our recent studies. The explosion mechanism of coconut supernovae is a long-standing program. And 4 years after the calculation, Harvard failed to reproduce the explosion. And here, I showed the basic picture of the coconut supernova explosion. And here, in the interior of the stars, more massive than 8 solar masses, iron core forms during the final stage of the stellar evolution. And the iron atoms cannot produce energy by fission. So once the iron core grows to about the mass of the sun, then the core becomes unstable and cannot provide more sufficient support against the inward force of gravity. That leads to gravitational collapse, and the collapsing core gets crushed into an extremely dense object, protoneutron star, and which slows the collapse and drives a shock wave into the falling matter above. And if this bounce shock wave reaches the surface of the star, then the star will explode. But the problem is that the rebound is not so strong to explode. So in this case, we need some mechanism to produce the shock reviver. Then we now know the observation of neutrinos from SN 1987A was a big step to understand the explosion mechanism. For example, this is inside of the super Kamiokande in Japan, and this is a neutrino signal from the Kamiokande, and these neutrinos comes from the innermost region of the exploding star. Probably need to explain how the progenitor star explode. And recently, some groups have succeeded to explode stars in simulations, and then some asymmetric effects seem to help the explosions. Here, the important mechanisms are neutrino-driven convection and some instabilities like SASI. For example, in this video, we can see the evolution of bubbles made by the neutrino heating. Those bubbles make high-entropy plumes and accelerate the supernova shock wave. And such asymmetric effects are known to be a very important process to explode the stars. And however, there is still no strong observational evidence of these asymmetric effects. We have a direct neutrino observation from SN 1987A, but this observation is not enough for explaining these asymmetric effects. So here, our motivation in this study is to search for some observational evidence of such an asymmetric effect. Sorry. Yes. Yeah. we would like to search for such evidence of the asymmetric effects. And the neutrino heating makes some convective bubbles, and some of the biggest high entropy bubbles can develop into the later instability on the larger scale at the later stage of the explosion. And in our study, we focused on it. For example, this is a supernova simulation at the later stages. We can see iron-rich finger like this. These came from the neutrino convection effect, and then we should observe those structure rather high entropy and iron rich. And if we could find such features in the supernovae or supernova remnants, it will be a strong evidence for examining the asymmetric effect by the neutrino heating. On the other hand, in the case of supernova observations, we could observe those events as point sources like this. So it is difficult to evaluate the shape. So in our study, in our new viewpoint for this is some asymmetric structure came from the supernova neutrino interaction. Should have a different elemental composition by those nucleosynthesis. And also those features can be observed by the supernova remnants. And we focused on this for the first time and have obtained our conclusive evidence of that. And before talking about the detailed result, I would introduce the nucleosynthesis of a quark supernova. Actually, the outputs of a nucleosynthesis is different from star to star. For example, in the case of massive stars, those progenitor stars have different masses, and if we change those parameters, then we could obtain the different nucleosynthesis outputs. So we need to follow the evolution of each progenitor star to compare with the observations. So in that case, we have large uncertainties on those calculations. On the other hand, in the silicon bonding layer, that is here, I will explain this part later, but in the silicon bonding layer, that is the innermost layer of the exploding star, we have only a few physical parameters to determine the elemental composition. For example, peak temperature and peak density during the nuclear burning processes, and also electron fluxing, Y sub E. This is a neutron to proton number ratio, and also time evolution of these parameters, thermal evolution. Only these can determine the elemental composition in the innermost layer. This is called nucleus, also called as the nuclear statistical equilibrium. If we could use this, if we could measure abundance in the innermost layer, we could estimate the physical parameters on the central region of exploding stars. For example, this is an example of the 1D nucleosynthesis calculation for quark supernova. And the horizontal axis shows mass radius. Smaller number means the inner region of the exploding star, and the larger number shows the outer side of the exploding star. And vertical axis shows the mass fractions. And for example, silicon burning is start at around here. And then silicon is consumed by burning. And then silicon is converted to more massive elements, heavier elements, like iron and nickel, like this. And also in this layer, we can see some rare metals like chromium, titanium 44. And if we could measure those mass ratios, we could determine those parameters. But yeah, it was difficult to search for this other elementary composition at this layer until now. And our question is, can we do this using supernova remnants? And before talking our result, here I would like to introduce another important observation in supernova remnants. To investigate nucleosynthesis at the deepest layer of the exploding star, as explained in the previous slide, the observation of the radioactive titanium-44 were well known to be useful. This is because the synthesized amount of this isotope is known to be sensitive to the asymmetric explosion. I will explain the detail in the next slide, but asymmetric explosion have a high entropy environment on the central core of the supernovae. So if we could measure the amount of this isotope in the remnant, we could discuss those high entropy burning process in the central core. That is very useful method to probe the central activity in the supernova. For example, here I show the recent results from the new star observation. Here, this is Cassiopeia A, and this is from the SN9087A. Here, in the case of Cassiopeia A, they investigate the distribution of the titanium-44 like this, and they found the titanium-44 are located at the inner region of the remnant. And also, in the case of SN9087A, they detect the titanium-44 like this. But in the case of SN9087A, it is difficult to investigate the distribution. So they only discuss the Doppler effect of those lines. They found the titanium-44 has a redshift velocities, and probably those came from the asymmetric explosion for this supernova. So as discussed in these observations, titanium-44 is important because we can discuss the supernova central activities without a neutrino or gravitational wave observations. So we think those isotope was important. And actually, our question is there any other elements too sensitive to such a high entropy burning processes? And the answer is yes. We have other elements too sensitive to high entropy regimes. And the central region of a core of supernovae has a low density. And in this case, alpha particle-rich nuclear statistical equilibrium is realized. If the density is low, the expansion time is fast. Then nuclear statistical equilibrium predicts a significant light particle abundance, especially alpha particle. And then when the temperature falls, the alpha particles cannot be converted to fast enough to iron nuclei. Here, the equilibrium is terminated by the excess of the alpha particles, and they're captured by nuclei during freezeout will alter the nucleostatistical equilibrium composition. In this case, some elements, intermediate alpha elements produced by alpha capture, have also sensitive to the entropy during the explosion. So not only the titanium-40, for other alpha elements like stable titanium and chromium should also exist in the high entropy burning regimes. And if we could investigate those elements, we could discuss the high entropy burning regimes during the explosion. And these observations should be strong evidence of the high entropy burning process. And actually, this is our motivation in our recent result. Then let's talk about the actual observation. And to verify this, we use the observation of the supernova remnant Cassiopeia A. Here I showed the optical image of the Cass A, and the color is not real, but distribution of the optical emission is like this. We can see some asymmetric structures and filament structures like this, but the shape is almost circular. But if we see this remnant with X-rays, we can see these distributions. Blue color shows silicon-rich ejecta, hot plasma, and also light color shows iron-rich ejecta. We can see this jet-like structure, but today I do not focus on this structure. But here we can see the iron-rich ejecta, and this is important for our study. And here we can see protruding iron-rich ejecta, and we think probably that would be the high entropy plumes from the exploding from the central core of the explosion. This is because the iron should be produced at the innermost layer of the exploding star. So this structure must be produced at innermost area, and after that, some processes pushed out this structure to the outer side of the remnant, and we suspect this could be the high entropy plumes that may be produced by the high entropy, maybe produced by the neutrino heating. And so then we investigate elements in this structure using a X-ray spectroscopy. And as a result, we found the titanium and chromium that thought to be produced in the high entropy region in the exploding star. This is the first detection of these elements at this region. And this is the X-ray spectrum from the iron-rich ejecta. We can see strong iron line here, and also we can see some signals from titanium and chromium like this. And we fit those lines with the thermal models. Then we found the significance level is above 5 sigma. And using this spectral analysis, I estimate the element mass ratio between chromium and iron, and titanium of iron. And then I compared those results with theoretical calculation over 1D quark supernovae. Then this axis shows chromium over iron mass ratio, and this axis shows the titanium over iron mass ratio. And the curved area shows the observations, and this is also same part. But curved point shows different models, theoretical models, and the above panel shows in the case of a neutron, rich ejector, and the bottom case is for the proton-rich ejector. And here we can see the our result is ruled out. Our result rules out the incomplete silicon burning layer for the origin. Incomplete silicon burning layer is just above the alpha-rich freezeout. In that region, the titanium and chromium was produced, but the mass ratio indicate we can rule out those origin. And we found the observation can explain well by the alpha-rich freezeout composition like this. Here, circle data and square data indicating different electron fraction at that layer. For example, in the circle data, we use y sub e equal 0.499. That is for the sub-solar metricity model for the Cassiopeia's progenitor. And also square data indicating the y sub e equals 0.5. 0.5 means neutron, the same number between the neutron and protons. But in the case in the progenitor star, it is difficult to realize the y sub e equals 0.5 because in most cases, interior of the star, during the neutronization should be progressing during the stellar evolution. So probably if we adapt this, in the case of that we adapt this value, we need some modification of the y sub e to the 0.5, and our neutrino interaction can modify this electron fraction to the 0.5. So probably this might be effect from those effects, but that is not so strong conclusion. And also we compared with the proton-rich ejector case here, and then we found that our observations can be well explained by the theoretical calculations. Here we calculate some nucleosynthetic outputs, assuming the very high temperature, that is 10 gigakelvin, and also extremely high proton-rich ejector, like y sub e equals 0.55. There's y sub e at 0.55 cannot be realized in many cases. Just only realized by the strong neutrino processed ejector at the inner core of the supernova explosion. So using this comparison, we conclude that probably this iron-rich ejecta should be produced from the innermost area of the exploding star, and then probably the ejecta was heated by the neutrino radiations. And then, yeah, this observation indicates that the iron-rich ejecta could be the high-entropy ejecta plumes from the neutrino convection. And I would note that in current phase, we cannot completely dismiss the production of the neutron-rich region like this, but our results support the mass fraction in the innermost region agree with the high entropy ejecta plumes from the neutrino convection. That is the main result in our Nature paper. And also, I introduce our ongoing project that is related to the observational verification of the neutrino process. Neutrino effects are poorly understood, and both observationally and theoretically. And our question is, can we discuss those effects using X-ray observations? And now we are collaborating with the theoretical researchers and considering those effects. And here, if the neutrino matter interactions occurs in the innermost layer, then there should be a neutrino process. This is a neutrino nucleosynthesis. And then the most important process in the neutrino process is spiration by neutrinos. For example, some nuclei hit by the neutrinos, then proton and the neutron is excited and ejected like this. Then the element will be changed to another elements. And if we could observe this in the remnant, we could discuss the neutrino process in the exploding stars for the first time. And now we focused on this reaction. For example, innermost region, the nickel 56 is the most abundant. So if the neutrino hit this nickel 56, then our proton will be ejected. Then this nickel 56 is converted to the cobalt 55. And this cobalt 55 has finally become manganese 55. And this is a stable element. And this effect should be very significant at the innermost area. For example, this is a nucleosynthesis calculation on the central region over quark supernova. And if we do not consider the neutrino process, and then our mass of the manganese is very low like this. But if we include the neutrino process in the nucleosynthesis calculations, then the amount of the manganese increased drastically like this. And we think we can observe this effect using X-ray observations. And yes, now we're testing this using our iron-rich ejecta in Cassiopeia A. And as a result, we found that we cannot explain the observation without the neutrino matter interactions. Here I showed manganese over iron mass ratio and the titanium over iron mass ratio. And the cloud area shows the observational range. And if we assume the nucleosynthesis without the neutrino process, then this is there's calculation. In this case, we could not explain the observations because in the most region, in that region, we cannot produce a large amount of manganese. On the other hand, if we include the neutrino process, the theoretical calculations are now in the range of the observations. That is very interesting because we cannot explain this observation without neutrino matter interactions. Also, these calculations assuming the proton-rich ejector. In this case, the effects of the neutrino process is much lower than these cases. But to create the strongly proton-rich ejector, we need strongly neutrino process to ejector. So in this case, we also need neutrino matter interactions. So using both models, we can conclude actual observation of supernova remnant allow us to discuss neutrino matter interactions for the first time. And we are now preparing this paper to be submitted some journals. And the other future works, I do introduce some things. And now we are thinking to discuss the distribution of the entropy and the Y sub E in the exploding star. And I would like to compare with those parameters with the theoretical calculations. For example, this image shows a multidimensional supernova explosion models. Then we can see some asymmetric structures. Those are caused by the asymmetries during the explosions. And this side shows the electron fluxion. And the bright color means proton rich. And this side shows the entropy, and the bright color shows a higher entropy. Then in the simulations, our high entropy region has a higher electron fluxion. That means a proton-rich ejector. So if we could investigate those elements like titanium 44, titanium, stable titanium, chromium, iron, and nickel at the same time, we could discuss those physical parameters around the supernova energy. For example, we preparing these calculations. Here, if we could compare the mass between the intermediate mass element, mass alpha elements, and the iron, then we could evaluate the entropy. For example, in this plot, we showed titanium over iron or chromium over iron mass ratios in the peak density and peak temperature plane. And if we increase the high entropy, then we can increase the yields of those elements. And using this mass ratio, we can discuss entropy in that supernova. And also, if we compare the neutron-rich element with the iron, then we could evaluate electron fluxion like this. Here, this side shows a proton-rich ejector, and this side a neutron-rich ejector. So using these relations, we could investigate the physical parameters around the central engines.
We have 3 minutes left, including questions.
Okay, yes. This is last choice. And we we are now preparing some actually calorimeter missions from the 2020s to 2030s. And using this actual calorimeters, we can obtain a very high energy resolution spectrum like this. This red color shows a Chandra, and this black color shows a quasar. Using these missions, we could measure rare elements more accurately, like this. And we hope using this observation allow us to improve our current result. And also we expect to detect some odd Z elements from remnant. That will be very useful to discuss some specific nucleosynthesis calculations. And yeah, we hope this future mission help us to understand the supernova explosion mechanism. Yeah, that's it. This is summary. Other SNRs have a limited sample size compared to the supernova. It allows us to measure the distribution and the composition of the elements at the center. And we think this is a very useful method to prove the explosion mechanism of supernovae. And a discovery of the structure from the deepest part of the supernova explosion allows us to discuss in detail the activity of the explosion center, and including the new influence of the neutrinos. And that will be a very new result. And in the future, the combination of the observational research using the future X-ray missions and the theoretical researches will bring us much closer to understanding the mechanism of the supernova explosion. Yeah, that's it. Thank you very much.
Thank you very much. I would like to ask everyone to unmute themselves and give them a round of applause.
Thank you.
Thank you. So we're nearly we're close, very close to the hour. So does anyone have any quick questions? Discussions? So I had a naive one. So you compare a lot of these results with 1D calculations, but yet you're trying to discuss the asymmetry of supernova remnants. So how good is these like 1D calculations when you're trying to focus on local?
Yes. That is a good question. At the innermost layer, in the silicon burning layer, actually, the alpha rich freeze art can be determined. The composition in the alpha rich freeze can be determined very few physical parameters, and that is not affected by the multidimensional effects, but thermal evolution of the structure will be much different from the multidimensional model. Thermal evolution is much different between the multidimensional model and the 1D model, and that could change the element abundances. But we also discuss others in that paper. We also examined the different thermal evolution of the ejector, and then calculate the nucleosynthetic outputs. And then even if change those different thermal evolution, our conclusion was not changed. But probably we could not discuss the absolute values. What is the actual entropy or something? Yeah.
I see. We have another hand up from Daniel.
I was just curious. I mean, how sure are you that this explosion is from one star? Is that known for Cass A?
Sorry.
Are you sure that the explosion was from one star, not two?
Yeah.
Do you
How are
mean
you
like
sure?
you think it's like a merger or something?
Well, is this a type 1A? This Cass A? No.
This is a quark supernovae.
So let me ask my question the other way around, which was, I was puzzled because you were pointing out at the start of the talk that the type 2, the core collapse remnants seem to be more asymmetric than the type 1A remnants.
Yeah.
So I was puzzled by that because
Sorry,
you mean
you're dropping out.
well, why rem more metric than the core collapse?
sorry, sound is blocking.
We could only hear why. I think his question is why are core collapse more asymmetric than type 1As? Is it?
Yep.
I think in the case of type 1A, there is not so strong activity in the central region. That is just a thermonuclear explosion, and the explosion will start in the center. If ignition that are central core, the shockwave will expand uniformly. In that region, probably that should be some instabilities, but not such an effect is not so strong to distort the shape. So I think, but in the case of quark collapse supernovae, we need strong asymmetries during explosion, and that will be main reason why there's differences of the ejecta distributions.
Thank you.
Is that okay?
Daniel says thank you, very helpful in the chat. Are there any other last questions? If not, let's thank Toshiki again. Thank you very much for this very nice, exciting talk for your latest results. Let's wrap it up here. We have another Astro seminar next week, so please keep an eye out on your calendar. Okay, then see you all.
So bye. Thank you.